Hey everyone, and welcome to The Explainer. Today we're literally peering under the hood of machine learning. We're going to look at the mechanics of how we keep AI models reliable out there in the real world. We constantly hear about AI doing these absolutely incredible things, right? But how do we actually stop these massive, complex mathematical engines from just completely flying off the tracks? Well, the answer lies in a fascinating set of tools known collectively as regularization.
Okay, let's dive into this. How exactly do we stop an AI from just memorizing things? It's genuinely one of the highest stakes problems in machine learning today. We call it overfitting. See, high-capacity deep neural networks, they have immense power. But without the right constraints, an AI will often just take the lazy route. It uselessly memorizes its training data, including all the random noise and weird outliers, instead of actually learning the general, underlying patterns we really need it to understand. Basically, it becomes a brilliant parrot, but a terrible thinker.
So, here's our roadmap for this toolbox tour. First, we'll look at the overfitting problem. Second, an introduction to weight decay. Third, the big matchup, L1 versus L2 regularization. Fourth, we'll check out dropout and label smoothing. And finally, choosing the right tool for the job. Don't worry, we're going to break all this dense math down into a super clear, step-by-step journey.
All right, starting with Section 1, the overfitting problem and how we go about constraining the machine.
So if we want our models to stop fitting random noise in the training data, we absolutely have to actively manage their complexity. Think of regularization as the necessary guardrails for our algorithm. By narrowing down the set of potential networks that the training process can even explore, we keep the AI on track. We're intentionally limiting its capacity to learn those hyper-specific, totally chaotic mappings. Regularization helps us maintain that delicate balance, what we call the bias-variance trade-off. It ensures we don't underfit the data with a model that's too simple, but also that we don't overfit it with a model that's wildly complex.
Moving right along to Section 2, Introduction to Weight Decay.
Weight decay is the very first major tool we're going to pull out of our regularization toolbox today, and honestly, it is exactly what it sounds like. During the optimization process, we simply add a penalty term to the model's loss function based on the magnitude of its weights. Basically, we're mathematically telling the model, hey, don't let any single parameter get too large unless it's absolutely necessary. By driving the optimizer to favor smaller, much more stable weights, we naturally constrain the whole model from reacting excessively to random outliers or noisy data points.
So, the crucial point is Occam's razor. You've probably heard of this philosophical principle, right? It states that simpler hypotheses are more likely to generalize well. Well, weight decay is essentially the mathematical embodiment of Occam's razor. By heavily penalizing those massive weights, weight decay acts as a strict constraint. It forces the model to find a compact, simple solution. It restricts the optimizer's search space, which smooths out the loss landscape so our model's predictions remain rock solid and stable.
Now, you might be wondering, why does model simplicity matter that much? Well, consider the absolutely massive scale of 200 million dimensions. Imagine a housing data set spanning the entire globe. If you bucket latitude and longitude into just 1 minute granularity, you get thousands of dimensions. Cross those features together to pinpoint locations and suddenly, boom, you've created around 200 million dimensions. And here's the real kicker. Most of those represent the middle of the ocean or completely uninhabited deserts. They hold literally zero meaningful data. Paying the RAM and compute costs to store and process 200 million mostly empty dimensions is a massive waste of resources. We desperately need a way to drive the weights of those totally irrelevant features to exactly zero.
Which brings us to Section 3, L1 versus L2 regularization. The main event.
To understand how these two heavyweights actually differ, let's use a quick corporate manager analogy. Think of L1 regularization as a ruthless editor or a really strict manager. Because of its diamond-shaped mathematical geometry, it has these sharp corners that literally trap weights. It targets useless features, like those empty ocean coordinates we just talked about, and it straight up fires them, driving their weights to exactly zero. By contrast, L2 regularization is more like a smooth, highly diplomatic manager. It operates on circular geometry with nice smooth curves. So instead of firing anyone, L2 evenly reduces everyone's hours. It shrinks all the weights proportionally, but without eliminating them completely.
And this brilliantly illustrates exactly why that happens under the hood. The difference between the two happens precisely because of their mathematical penalty functions. See, L1 penalizes the absolute value of the weights, which means its derivative is a constant. It just subtracts a constant amount every single time. L2, however, penalizes the squared magnitude of the weights. So that means its derivative is proportional to the weight itself. Larger weights get a much bigger penalty, while smaller weights get a smaller penalty. Because L1 subtracts that constant amount, regardless of the weight's size, it actually creates a discontinuity at zero.
If a subtraction forces a weight to cross from a positive to a negative, L1 just snaps it to exactly 0. And that's what makes L1 an incredible feature selector. It creates what we call weight sparsity. If you've got a super wide model with tons of irrelevant dimensions, L1 efficiently ignores them for you, giving you a really sparse, beautifully memory-efficient model.
Now, let's flip over and see how L2 builds a completely different outcome. L2 acts as the uniform shrinker. Because its penalty is proportional to the weight itself, it functions a bit like Zeno's paradox. It removes a percentage of the weight at every single step. And as Zeno knew, if you keep removing a percentage of a number, it gets infinitely smaller but never quite reaches exactly 0. This results in an incredibly smooth, uniform distribution where all the features share the load. It makes the model highly precise.
All right, let's look at Section 4, Dropout and Label Smoothing.
Let's open up the final compartments of our regularization toolbox to look at some modern techniques designed specifically for larger, more complex deep neural networks. First up is Dropout. Okay, so if you had literally unlimited computing power, the absolute best way to prevent overfitting would be to train dozens of completely different neural networks and just average their predictions. But, obviously, that is incredibly expensive. Well, Dropout provides a brilliant shortcut. By randomly dropping some neurons during each training step, it forces the network to constantly adapt without ever relying on any single node. It mathematically simulates that massive computational feat of averaging multiple architectures but completely bypasses the actual time or data cost. It's a real game changer.
Next is label smoothing. Normally, in classification tasks, we train an AI with absolute certainty, a hard 1 for the correct answer and a 0 for everything else. But absolute certainty, that leads to overconfidence. Label smoothing takes that 1, lowers it slightly, say down to 0.9, and redistributes that remaining 0.1 across all the other classes. It fundamentally stops the model from just outputting absolute 1s and 0s.
So when do we actually use this technique in practice? Well, label smoothing is perfect when you have a massive number of classes, like if you're classifying thousands of different images, or when your labels might just be noisy and uncertain to begin with. By injecting just a tiny bit of uncertainty into the training process, we actually cure the AI of that dangerous overconfidence. It makes its predictions much more probabilistically sound and way more robust in the messy real world.
Finally, we arrive at Section 5, choosing the right tool.
Now, what's really interesting about this slide is how we can simplify everything into actionable, practical advice. You should definitely use L1 when you are answering the question, what? If you're unsure which features actually matter, or maybe you're deploying to a mobile device and you desperately need fast inference with sparse vectors, let L1 do the heavy lifting and feature selection for you. On the other hand, use L2 when you are answering how much. If you already know all your features matter and you really need to capture Euclidean distance for the highest possible prediction precision, L2 is absolutely your go-to uniform shrinker.
As we wrap up this explainer, I want to leave you with one final, totally provocative thought. Which guardrails will you choose to keep your models grounded in reality? Because at the end of the day, an AI without constraints isn't really learning, it's just memorizing data. Mastering these tools, weight decay, L1, L2, dropout, and label smoothing, that's the absolute key to building artificial intelligence that truly understands the complexities of our world, rather than just acting like a brilliant parrot. Thank you so much for joining me to explore this fascinating topic. Keep building, keep constraining, and we'll see you next time.